Everyone, it's Mr. Canfield. This is for AB Calculus. This is Chapter 15, Part 2. Last time we did Chapter 15, Part Unfocused. There we go, okay. Chapter 15, Part 1 on continuity. Today we do differentiability. So, differentiability is a long word, but it's got a pretty basic root word in it, differentiate, which just means take the derivative of, right? So to be differentiable means you can take the derivative of it. So in picture form, differentiable functions are smooth. In order to be differentiable, you already have to be continuous. So anything that's differentiable is like a subset of that which is continuous. All right. So there's some wordy definitions here. I think they bear reading really quick. Differentiability at a point. A function f of x is differentiable at x equals c if and only if f prime of c exists. So c is some number, and it's saying if f prime of that number exists, then the function's differentiable there. Like, it's just the definition of what it means. So, differentiability on an interval. A function f of x is differentiable on an interval from a to b. If you've never seen this notation before, you probably have. It's called interval notation. It's just meaning from a to b. It's differentiable from a to b if and only if the derivative for every number on that interval exists. That's what this is saying here. If f prime of c exists for every value of c in the interval a to b. A differentiable function. A function f of x is differentiable if and only if f prime of c exists for every value of x equals c in its domain. So real quick, we've used this phrase if and only if. Actually, all three of them have if and only if. If and only if is it's a mathematical thing that works both ways. So like if the left is true, then the right is true. And if the right is true, the left is true. Like they make each other true. And if you're like, well, yeah, that makes sense. This is different than like, if it's a cat, it has 4 legs. That's not an if and only if situation. Because if something has 4 legs, that doesn't mean that it's a cat. So if a function is differentiable, its derivative exists. If something's derivative exists, then it's differentiable. So that's why we use the phrase if and only if. All right, so some differentiable functions that you are allowed to know are differentiable forever. Polynomials. Every polynomial is differentiable. Sine and cosine are differentiable. Exponential, like e to the x, is differentiable. These are all differentiable for all real numbers x for their entire domain. They have no problems. All right. So we've got some examples. So when is something not going to be differentiable? Well, the first case where something's not going to be differentiable, if f of x is not continuous at x equals c, then it isn't differentiable. I guess I should say then f of x. So if f of x is not continuous at x equals c, then f of x can't be differentiable at x equals c. You have to be continuous in order to be differentiable. But let's look at, we have 2 main pictures of non-differentiability. So really any smooth curve, like pretending that I can draw well, any smooth curve like this counts as differentiable. It's not until we run into situations like this or like this both of these are considered not differentiable. And if you recall, all the way back to the first lesson of the year, okay, second lesson of the year, we talked about tangent lines. And we had some pictures that we drew in these tangent lines where we were trying to draw the tangent line at these dots. And we were like, we can't, because there's like an infinite number of tangent lines that I could draw. And so we say it's not differentiable at those points. Yeah, still not differentiable at those points. We just didn't use that language. Oh, I closed the book. I lost my spot. No. Oh, I know we're on chapter 15. Found it. Okay. All right. So a word that we have for this one that looks like a little bit like a seagull, it's called a cusp. This guy's called a sharp point. These are more informal names. All right, so I'm back. Sorry about that. So the two examples that we have here. This is a cusp right here, and because of that cusp, we could say that f prime of 0 is dne, or does not exist. And similarly here, g prime of 0 is dne. So, okay. So, graphically, it's easy to tell, but when we have piecewise functions, it's a little bit harder, and we start out actually doing it the same way that we did in continuity. So the first thing I want to do, like in example 8, or A in 8, is if I'm trying to determine if this is differentiable when x is equal to 2, well, I guess he's saying determine whether f of x is continuous and differentiable just in general. So these are both polynomials. So we know that in general they're both continuous and differentiable, but are they continuous and differentiable where they meet? So to find out if they're continuous, we set those equal to each other. When x is 2. So we plug in 2. So I got 14 minus 12. I got 2 is equal to 2. Okay, so we know it's continuous. That means it's possible that it's differentiable. To find out if it's differentiable, we set the derivatives equal to each other. So the derivative of the x squared minus 6x plus 10, what is that? 2x minus 6. 4 minus x is going to be negative 1. And it's when x is equal to 2. So we plug in 2. So 2 times 2, 4, minus 6, is that negative 1? No, it's not. So it's not differentiable when x is equal to 2. And what we're doing here is functions are differentiable because the derivatives, as we approach a point, the derivatives approach the same derivative. So the problem here is, as we approach 2 from the left, the derivative approaches negative 2. And as we approach it from the right, the derivative approaches negative 1. So since those derivatives don't match up, it's not going to be a smooth curve there. Then he tells us to sketch the function. No. All right, let's see. Part B. So we're going to set x squared plus x minus 3 equal to negative x minus 4 when x is equal to negative 1. Let me just back up really quick. So what we're doing here, just in case you missed it last time, the idea is I have these two continuous polynomials. I'm trying to find out do we have, so this one has a closed dot because of the equal to. This one has an open dot. We're trying to find out when we get to x equals negative 1, do we have a situation where, like, this is a parabola, right? Where the parabola comes in with a closed dot, and does the other one go off like that? Or is it actually connected there. That's what the continuous is asking. And the differentiable is asking, do we have a smooth transition of power such that there's no noticeable change? Or is it abrupt? And in the last example, it was abrupt. Actually, I can even show you that. Yeah, on the main screen. So, I always forget. There's a way to graph piecewise functions using the calculator. It's not that big of a deal. Let me zoom standard. So these were changing when x is equal to 2. So, is it like this? I think it's like this. Yeah, okay. So, yeah, you put the function in parentheses, and then you put another parentheses, and you say x, and you go over here to test, so it's second, and then test. And you can use the symbol that you need. It only tells you so much, though. But hopefully you can see that that's not super smooth. You can kind of tell where the change happens. So if we look at this next one, x squared plus x minus 3 when x is less than or equal to -1, and then it's just negative x minus 4, so it's the same thing the way I wrote it. So now that change is a little bit harder to tell exactly where it happens. So I'm going to guess that this one will work. But no need to guess. Let's plug it in. So -1 squared is 1. -1 is 1. So I got -3 is equal to -3. So it is continuous. Now I'm going to do the differentiable check by setting the derivatives equal to each other. Right, derivative 2x plus 1, and then -1, and then when x is equal to -1, so that's -2 plus 1 is equal to -1. I get -1 is equal to -1, and so that means when x is -1, their slopes are equal to each other. And so that's why there's this smooth transition from one to the other. All right. So this is continuous and differentiable. Since it's continuous and differentiable at this switching over point, and on their own they're both continuous and differentiable, then the whole thing is continuous and differentiable. Whereas the first one, we can say that this first one, A, we could say is continuous. All right, you know what? Let's use the language, right? We can say f of x is continuous for all x I guess we say f of c is continuous for all c where c is contained in all real numbers. That's not that helpful, is it? So you can say f of x is you can probably just say f of x is continuous for all real numbers. And then we can say f of x is differentiable for all real numbers except x equals 2. And then another way that we could say that, we could say this is like a exclusionary way to say it. Exclusionary. We could say f of x is differentiable on negative infinity to union to infinity. So you can say negative infinity to 2, union 2 to infinity. Well, that's, I'm trying to rush a little bit, and that's a little bit too much. So let's just this is what happens when you rush. You wind up taking longer. So you'd say f of x is differentiable on negative infinity to 2, union 2 to infinity. All right. Let's see what our next one is. Oh, good. Nice, simple problems. All right. So if I plug in 4, right? Am I underthinking this? 2 minus, that's 0, right? Is 2 equal to the square root of 9? So since it's not continuous, at 4, we also know it's not differentiable at 4. Remember, because in order to be differentiable, you have to already have been continuous. So cool. So it's not C or D when x is equal to 4, but is it continuous everywhere else? Is 2 minus the cube root of x minus 4 continuous everywhere else? And you might want to say, well, negatives aren't going to be okay here, but the graph of a cube root, well, think about this. What's the cube root of negative 8? We know the cube root of 8 is 2, right? Because 2 times 2 times 2 is 8. The cube root of negative 8 is actually negative 2, because negative 2 times negative 2 times negative 2, it's that triple negative. So this is actually defined everywhere. This is continuous everywhere. Is it ever not differentiable? And actually, yes, cube roots, if you think about this, the cube root of x is equal to x to the 1/3. And so even though it's continuous everywhere, there are places where the derivative of this does not exist, because the derivative of this, we bring the 1/3 down front, right? We have x to the 2/3 down here. So now zeros of this, which in this case is just 0, but zeros of the insides, which in this case would be 4, are going to wind up in the denominator of the derivative. And so when x is equal to that number, the derivative won't exist. Odd roots are going to run into that problem. And it's the place where the graph does like this. It winds up essentially being vertical for just a moment right there in the splitting point, the 0 of the radical. So yeah, that's going to be a problem for that. Let's see. So he says more or less everything that I'm doing. He says it up there. All right. I'm being a little bit lazy. I should actually do this problem. Okay. So if we take the derivative of the left-hand side, the 2 turns to 0, and then minus 1/3, that stuff to the negative 2/3, and that's going to be x minus 4 stays on the inside. What's the derivative of the inside? Oh, it's just 1, so it just stays. And then the derivative of this is going to be 1/2 root the insides, right? Because I've memorized the derivative of square roots. Square roots always do 1/2 root the inside. That's the derivative. So this one isn't defined when x is equal to -5, but if you look down here, well, even less than -5, because you can't take the square root of negatives. But the thing is, this says x is greater than 4. So this is 4 and more. And we're actually plugging in 4 right now, and that's where we got our problem, because this is 1 over 3. This is 1 over 0, which is not okay. And so undefined does not equal 1/6. So it's not differentiable there, but it'll be differentiable everywhere else. All right. D, more of the same. Ooh, x is 0. We love doing sine and cosine when x is 0. So is sine of 0 equal to 0? Or is cosine of 0 equal to 0? If you don't know, I'm not telling you right now. I want you to go look it up, or I want you to figure out a way to tell yourself, because it's really, really important that you know which one of these is 0 and which one of these is 1. So crap. The only way for me to keep going is for me to tell you. It's not this one. Okay. So sine of 0 is 0. So we wind up having 0 is equal to 0, so we know it's continuous when x is 0. And earlier I mentioned that sine is a continuous differentiable function. So if I take the derivatives, I get 1 minus 6x. Is that equal to cosine of x? And we have x is equal to 0. That's 1 minus 0 is equal to 1. So yes, it's actually continuous there as well. I want to see what this looks like. That's got to be kind of weird looking, right? If I haven't said this before, if you are in physics or a few different classes where you use trig, you probably are using degrees. We use radians in here. Make sure that you've switched back to radians anytime you're going to go do trig. There's a... Whoa. That was sitting under one of my papers while I've been working. So yeah, let's see what this piecewise function looks like. So second math brings up this test menu. There's a lot of cool stuff you can do with this. I'm also planning on filming a video. Oh yeah, I'm supposed to be doing their derivatives. I'm planning on filming a video where I show some of the tricks of the trade with the programming language in the calculator. So keep your eyes out for that if you're interested. Maybe I'll make its own playlist or something. If you hear the snoring, that is Rosie. She is snoring in her crate right now. Rosie, our dog. All right, so at 0, we should see a, whoa. What? Did I make a mistake? Oh, right. No, I am graphing the originals. So the derivatives do equal the same value there, but the derivatives don't look interesting. The derivatives look scary. Here's the original. So here we should see a nice smooth, oh yeah, there you go. Nice smooth transition of power. It looks like it's one continuous function. Sorry, one differentiable function. It doesn't look like two different ideas. All right. And then we get to 9, which is a wonderful AP question, an AP style question. I've seen this on many an AP exam. Find the values of a and b that make the function f of x differentiable. Well, remember, in order to be differentiable, you have to be continuous. So a says ax squared plus 1 has to equal bx minus 3 when x is equal to 1. But the other thing that also has to be true, wait, hold on, let's plug in 1. So a times 1 squared is a plus 1, b times 1 is b minus 3. Okay. So this has to be true. Oops, minus 3. But the derivative And a and b are numbers, right? So the derivative is going to be 2ax. And the derivative of bx minus 3 is just b. Wait a minute. So that means that 2a is equal to b. Wait, so I have a plus 1 is equal to b minus 3. I also have 2a is equal to b. I'm able to do substitution here. b is equal to 2a. And so I could actually go into this other equation, and where I see b, I could write 2a in its place. And so I could write a plus 1 is equal to 2a minus 3. And now this is a basic algebra question we can solve. I'll subtract the a from both sides. I'll add the 3 to both sides. I get 4 is equal to, a is 4. And then 2 times a is b, so that means 2 times 4. Let me, I never trust myself with these. I want to double check. So if I go back, I can go back to here, right? A plus 1, 4 plus 1 is 5. B minus 3, 8 minus 3 is 5. Cool, okay, we're there. And then I used that to get this, so it works there too. Cool. All right, let's do one more, because there is one more. If there were 12 more, we would do 12 more. Ugh. All right. So again, let me restate the reasoning here. If it's supposed to be differentiable, then there's the implied it's also continuous. So I can set them equal to each other and plug in 2. I can also set their derivatives equal to each other and plug in 2. So if I set them equal to each other, I get ax cubed plus 1 must equal b times x minus 3 squared plus 10 when x is 2. So that's 8a plus 1 is equal to, now here, well, that's going to be 2 minus 3, so that's negative 1, and then you square it. It's just 1. 8a plus 1 is equal to b plus 10, and then we also know the derivatives have to be equal to each other, so the left derivative should be pretty easy, 3ax squared. The right derivative, though, the 2 will come out front. Remember, a and b are just numbers. Inside stays alone, goes to the 1th power, multiplied by the derivative of the inside, which is just 1. 10 disappears. Oh yeah, x is equal to 2. So then 3 times a times 4 is 12a is equal to 2 times b times negative 1, negative 2b. So I guess I can solve this one and get b by itself, right? I can divide by negative 2 and get negative 6a is equal to b. So then I can go up here and drop a negative 6a in there. So now we have 8a plus 1 is equal to negative 6a plus 10. I'll add the 6a to both sides and get 14a is equal to 9. So I get a is equal to 9 over 14. That does not feel right. It feels like it should be a nicer number. And then negative 6a is equal to b, so that's negative 54 over 14. So b is equal to negative 54, because I just did the 9 times the 6 with the negative divided by 14. Those are both divisible by 2, though, so I could say negative 27 over 7. And if memory serves, these are right. They don't feel right, though, so I'm going to just show you what I would do if I was second-guessing myself a little bit here. I mean, one way to do it would be to go to these originals and actually plug in a and b where they belong. So, like, a was 9 over 14 x cubed plus 1. Oh wait, I need to I'm doing the piecewise version of this. We know x is less than or equal to 2. And then b was negative, nope, put up the parentheses, negative 27 over 7, parentheses, x minus 3, close squared, plus 10. It's a big mess, but theoretically, this should let us see if I mean, wow. Yeah, that looks pretty good. So that's probably not the way I would really test it. Probably the way that I would actually test it would be using my like A and B equations here. I know that like if this and this are supposed to be equal to each other. Oh wait, we have two different variables. Never mind, that's a horse of a different color. There's stuff that we could do, but I don't think it's worth your time, me explaining it right now. Okay, well, I hope this video was helpful. And now you should be able to go through and knock out the rest of the homework problems. I know it's a little bit repetitive going through some of these, but it is worth your time to see all the different types of examples, all the different things that you can run across. And let me know what I can do to help. So we still have a long way to go in calculus, but we're in this together. Have a great day, everybody. Bye.